Hi everyone, it's Adam again. Welcome back to Lab 4 video for ELEC 2507. Today we're going to be going through the BJT and fixed biased, self-biased circuits, and a BJT amplifier as well. All these circuits are going to be using the 2N3904 part number, which is an NPN transistor. You can go and actually look up the datasheet if you want to find all the characteristics that are given for this particular part. If I go to Google and search for the 2N3904, the first link will be to the datasheet. So here I can find the maximum and minimum beta numbers, which are given as the HFE numbers. So for a current of 1 milliamp, we can see our minimum is around 80 and our maxima is around 300. So our fixed bias circuits and our self-bias circuits, we want to use a beta value that's somewhere in between those, right? So in our pre-lab calculations, we're going to use a beta of 160. And then using that beta of 160, we can actually verify that in the lab once we're doing our calculations by measuring the current through the collector and the current through the base. Okay, so let's go ahead and get started. As you've done in previous labs, go ahead to See, Learn, navigate to the ELEC 2507 page, and find your station number. So if I'm on station 7, I'm going to navigate to Lab Stats, and then find my station, like I've done in the previous labs, find that IP, and connect to that station. That should be pretty second nature to you at this point, so I'm not going to show you all those steps, but go ahead and do that. And then again, you're going to want to make sure you do your pre-lab calculations for the fixed bias, the self-bias, and the BJT amplifier, as these will allow you to complete all the experiments. Without them, you won't actually have the particular resistance values that you need, and you won't even be able to do the experiments. So we also have a standardized resistor table here. Basically, we want you to use resistors that are in this table. So for example, in the first circuit, the fixed bias circuit, my R1 that I calculated was 200.86 kilo ohms. So I'm going to go in this table and look for the closest value to 200.86. And I can see here it's actually 200. So when I'm actually doing my report in Multisim, I'm going to use the value of 200 rather than 200.86. Okay? This is just to simulate an actual lab environment. In an actual lab environment, you'd have to put 2 or 3 resistors together to get that 200.86 kilo ohms. But in reality, you kind of just want to use one standardized value to minimize the circuit size and to minimize the cost of the design. So in all the circuits that I'm going to do here, the current, the IC current, is double your IC current. So I'm looking to achieve 2 milliamps of current through my IC branch. And for that, I have calculated certain values. So I'm going to go ahead and go back to Multisim, and I'm going to hook all these components up, like so, the way they're shown in Figure 1. And then I'm going to go ahead and actually change the component values to what was specified from my pre-lab calculations. So from my pre-lab calculations, I calculated that my R1 should be about 1.05 mega ohms. Oh, that wouldn't be right. So you need to go to the value portion and put in 1.05 mega ohms. But that might not be my closest standard value. So again, let's go look and see that I only have a value of 1 mega ohm. So actually put in 1 mega ohm here. Okay, Now on RC, I calculated my RC to be 5 kilo ohms. I'm going to go ahead and actually delete this RE because we don't need it for this circuit. So go ahead and directly ground the emitter. Once that's hooked up like so, you can go ahead and hit run, and you can measure the voltage at each of these nodes. Measure the voltage at the collector and measure the voltage at the base. Once I have the voltage at the collector in DC and I have the voltage at the base in DC, I can actually find the current through each of the branches by doing VCC, which I know is positive 15 volts, minus VDC, all over the resistance that I see there, right? So for the current through the collector, I would go 15 minus 4.16 to find a 10.84 voltage drop across this resistor here. And I'm going to divide that by 5K to find that I have a current in that branch of around 2.168 milliamps. And that is very close to what I calculated. Let's go and add a current probe if we want. And I can see that I verify exactly what I just calculated. So 2.168 or 2.17. Two significant digits. We can do the same thing now for the base. So you're going to note the value of the current through the collector being 2.168. And then you're going to note the current through the base. So I'm going to do 15 minus 0.685 in my case. And then I'm going to divide that by 1 times 10 to the 6th to find that I have a current through that branch of approximately 14.315 microamps. So now, if I divide IC 2.168 times 10 to the negative 3 divided by 14.315 times 10 to the negative 6, I'll find my actual value for beta for this transistor. And I'm calculating a beta that's around 151.44. So that's very, very close to what I calculated in the pre-lab. But as you can see, it's a little bit off from what we used. So from here, we're going to actually note the mode of operation for the transistor, and we're going to confirm the transistor's beta as we just did. So make sure you do both those things. And then we're going to reduce the RB, so the base value, by 20% to the closest standard value. So I have 1 mega ohms times 0.8, right? 0.80% of the original value to find that I have an 800K resistor is what I should be using. So let's go see if there's something around 800K. I can see my closest value is 820K in the standardized resistor table. So I'm going to go ahead and switch that to 820K. And from there, I can go ahead and stop and rerun the simulation. And now I can see that the mode of operation didn't really change for me, but in your case it will with the 20% change. So I actually just increased that change to more like 60% change, or sorry, more like a 30% change. And I went to 600K here. And now I can see that my DC value is actually way out of the operating point. So my VCE in this case is only 184 millivolts. And when the collector isn't higher than the base, which isn't higher than the emitter, then we know we have a circuit in reverse bias conditions. So last but not least, you need to comment on this particular circuit's sensitivity to the changes at the base. So when we made that change, how sensitive is this circuit to a change in the base resistance? So from there, I'll go ahead and actually remove these markers just so they don't clog up our sheet, and go ahead and stop the simulation once more. So for the next circuit, again, you should have values calculated for 1 milliamp and a VCE of 3.5 volts. Again, I've done mine to accommodate for current through the collector of 2 milliamps instead. So in this case, we already have our RC and our RE value given to us. So RC is 8.2K. And 3.3K. So basically, the way I did my calculations, I chose a value for R2, and then I calculated an R1 value from that. So I chose my R2 to be 60 kiloohms. And then my R1 value from that becomes approximately 200 kiloohms. Yeah, so actually I should have chosen a standard resistor value for my R2. So I'm actually going to switch that to 62K. So now I'll go back in here and switch this to 62K. And then from there, I calculate that my R1 should be around 181 kiloohms. So let's go find the closest standard value again and find that it's 180K. So go right here and switch this to 180K. And then we're good to hook up the circuit, I believe. So go ahead and get everything hooked up the way it's shown in figure 3. And you should be able to place voltage probes the same way we did before. Make sure that's probably down there. One on the collector. And also put one on the emitter as well. So let's go ahead and run the simulation now that we've got everything set up. And we can actually verify that the current through VC is actually IC that we calculated. So when I was trying to verify my operating point, I noticed that I had much less than the required current through my collector. So basically what I did was I reset RC and RE. You guys won't have to do this because your bias is set, but I'm looking to show you the case for 2 milliamps through the collector, so I had to reset my RE and my RC values. Now that I've done that, I have something close to double this resistance as the voltage drop across this resistor, which makes sense. That's what I want. I want around a 3.3 volt drop on this node here, and that will allow me to have exactly 2 milliamps through both my collector and my emitter. So what I'm going to do here is I'm going to adjust the value of R2 until it gives me that. So let's go down first and see what happens. When I go down, it doesn't look like it's giving me anything better. So let's go up. That looks a little better. Looks like the voltage is rising on this node, right? So let's go up to 90K. And now I'm exactly around 3.3 volts. Okay, so I have 3.3 volts, and I have almost exactly 3 volts between this node and this node, which if you look back at the specified calculations, they wanted a VCE of 3.5 volts. Mine's around 3 volts right now, which is well within the range of acceptability. And we can see that the voltage at this particular node, and then you can get the current into the base. So again, we can measure VCE, VBE, and now we can put in our current probes. We can measure that we have exactly 2 amps flowing through that node. We can see the current through our base, and we can find an estimated beta for this transistor. So let's go ahead and do that. So I have 2.09 times 10 to the negative 3 divided by 14.1 times 10 to the negative 6.
Hello, how are you?
So we know from question 5 that the operating point was achieved. So now we can go ahead and reduce both R1 and R2 by 20% to the closest standard value. And we're going to note the operation point and see if the current stays virtually the same. So from here, I can go ahead and drop this to around 144K. I'm also going to drop this to around 72K. And then I'm going to go ahead and rerun the simulation again. And I can see that the operating point hasn't really changed at all. So I can go back here, comment on the sensitivity of this circuit to changes in R1 and R2. We're going to note the transistor mode of operation and the new values of IC, VC, and VBE in this mode of operation. And we're going to compare the results of this experiment from the previous experiment and notice that the fixed bias circuit, self-bias circuit and the fixed bias circuit have a much different sensitivity to changes in the base resistance. So you're going to note those changes, and then we're going to go ahead and do the last section, doing the BJT amplifier. So again, I've done all these calculations already. I've found that my RC and my RE values should be equal, and they should both equal 2.5K. Go ahead and stop that simulation actually, and I'll delete all the probes like I did in the last section. Okay, and I can go ahead and hook everything up while we're at it. Why not? So we're measuring the unloaded circuit conditions here, right? Because there is no load. A load would be a resistor placed to ground, and there's no load here. So again, I've accommodated for an IC of around 2 milliamps I should have in my circuit, and yeah. So I'm gonna go ahead and build the circuit and verify the operating point in DC. So the R2 value that I've chosen here is 50K. And the R1 value then that comes as a result of that is approximately 116K. If I go back to the standardized table, I'll find 120K is what I'm going to have to use here. So go ahead and run that simulation again. Place your voltage probes. And you can get all your DC voltages. You can also get your currents. Right? So now I have my current through the base and my current through the collector. I can see I have approximately 1.36 milliamps. So it's not a great biasing circuit here that I set up. Let's see if we can adjust that by adjusting the value of R2. So let's increase R2 slightly to, let's say, 90K. Now we can see my DC current is around 2 milliamps. So once I did that increase, I'm at the required value that I've designed for. And I can see, just like was specified in the pre-lab, I have 5 volts between the collector and VCC. I also have 5 volts between the collector and the emitter, and I have 5 volts between the emitter and ground, like was specified in the pre-lab. The only difference in my circuit, again, is I have a current of 2 milliamps through my collector, where you guys will be looking for 1 milliamp through your collector. So look for the DC current. And once that's done, we can actually. So for this section here, the small signal gain and input resistance, it's asking us to find the gain at 1000 hertz, so 1 kilohertz. So the way we can do that is actually going in and adding a bode plotting device, right? So if we go ahead and add the bode plotter in to our circuit. All right, now that we have the bode plotter added to our circuit, we can see that this node is an on-page connector and it's labeled VIN, and this node here is an on-page connector and it's labeled VOUT. So that's the two nodes we want to measure between, right? So our output is VOUT, and our positive side of that output is actually this node, and our negative side is ground, right, where we're measuring between. Same with our input. Our input is measured between VI and ground. So let's go ahead and add 2 more ground nodes. You can either go just copy and paste, and we're just going to add those 2 ground nodes to the negative terminals of the input and the output, okay? And then once we're done that, we can go ahead, place on schematic, and say on page connector, and this will allow us to access VIN and VI, okay? We can go Control R to rotate that piece and put it there, and then this will bring up an on-page connector sheet, which will let you pick from everything that's already on your sheet. So you can go ahead and pick VI, double click on it, and it'll drag it right in there. So let's do the same thing here. So let's go place on schematic, on page connector, Control R twice to rotate it up, and then go VOUT. So now we're measuring the bode plot between VOUT and VIN, okay? So let's go ahead and run that simulation once more. And now we can see that the gain actually changes as a function of frequency, right? So let's go and increase the vertical scale a little bit more, just so we can see just above the x-axis there. And we can go over to 10 hertz, that's 10 hertz. 1 kilohertz, where is it? There, that's about as close as you're going to get to 1 kilohertz. And you can see that your gain is approximately -2 dBs. So from our pre-lab, we calculated that the gain in the passband should be around 0 dBs, right? Or 1 volt per volt. But in this case, we have just under 0 dBs, so we have -2 dBs in the passband. We're going to have to explain why that is. And I think it's very kind of clear from the resistor values that we had to change and the the standardized values that we had to use instead of the actual values that we calculated. So make sure you're just switching the scale a little bit to give yourself a nice looking waveform on the screen that actually looks decent in your report. And then you can go ahead and blow this up and take a screenshot of that bode plot for your report. It also wants us to adjust the input on the function generator from a 1000 hertz signal so adjust the amplitude of the signal until we notice that on the output oscilloscope we have a 2 volt peak to peak output. So the only thing we really need to measure in this case is the output node. So let's go ahead and stop this simulation once more. Place on schematic, on page connector, Control R twice, and bring that to the positive terminal of the oscilloscope. So we're going to measure the output voltage the entire time, right? Okay, so let's go ahead and place a ground node on the negative terminal as well, just like we did before. Copy and paste. Copy and paste. Then once we copy and paste that in, we can see that the oscilloscope is also hooked up to measure the output node. So let's go ahead and first we will switch this voltage on the waveform generator. So let's start at 10 volt peak to peak and just see what happens. So let's go ahead and run that. Okay, so when we first open up the scope, we can see that there's clipping going on, so that's no good. That's not what we want. Let's go ahead and adjust the scale slightly, make it a little more readable for us. And let's go back into the function generator and maybe switch that to 3 volts. So once we switch it to 3 volts, we can see the scope automatically updates in the function generator. That's what's nice, because we don't have to go restop and start the simulation every time. So we can go actually run a single sweep, and then let's place our markers in and find our peak-to-peak voltage here. We're looking to find an output of 2 volts peak-to-peak, right? So right now we can see that we're around 5 volts peak-to-peak. So let's go down to, let's try 1 volt here. All right. You can see at 1 volt, we're slightly below what we should be on our output, okay? So let's go 1.2 volts, maybe? Oh. 1.4. A little bit too high there. 1.2 is probably it. Yeah, so 1.25 or so. Yeah, we can see at around 1.25 we have exactly 2 volts peak to peak on the output. So let's go ahead and increase the scale, the division scale. Let's go ahead and actually bring that out a little bit so we only see about 5 waveforms is nice. Let's move those cursors around so we can actually show the outputs exactly 2 volts peak to peak. And we can take a screenshot of the function generator with the voltage that you used and the output voltage of 2 volts on both the on the output node. Sorry. So the last step it wants us to do is it wants us to get the current through the 10K resistor. So let's go ahead and place a current probe. And we can place that directly on this node here, okay? And we can see that the peak-to-peak current through that node is what we're looking for, right? We're looking for the small signal AC current through that node. We can see that it's 4.51 microamps. And we know what we're inputting into the function generator, right? We have 1.25 volts peak. Or 2.5 volts peak to peak, right? So we can place a voltage probe there to find the actual peak to peak. Or we just know that it's double whatever the peak voltage is here. So, that being said, we can actually do 2.5 volts peak to peak divided by 45.1 microamps peak to peak. And we can come up with a small signal input resistance for this particular amplifier. So from this calculation, I found that my small signal input resistance is approximately 55.25 kiloohms. So that's not a great amplifier. It's alright. It definitely could use some modifications to make it a little better. So last but not least, it wants us to increase the amplitude of VEI. So let's go ahead and go back to our input node, right? And let's look at our output node at the same time. So run a normal sweep again. Maybe bring this channel divisions down a little bit again because we're going to be getting an increased size in our wave. Okay, so let's go ahead and increase this to, let's say, 4 volts. At 4 volts, we can see we're already clipping on the bottom. Okay, so that would be an 8 volt peak to peak. Let's try 3 volts here. At 3 volts peak, we're not clipping yet. Okay, so it's somewhere between 3 and 4. So at 3.5 volts, we start to clip. Okay, so let's see, 3.4, we're clipping, 3.3, we're clipping, 3.2. It looks about 3.2 that we start to clip. Maybe even 3.1. Yeah, you could honestly argue that 3.1 is starting to clip because you can see the flattening of those curves on the bottom. So you're going to note that point. You're going to note the peak-to-peak voltage. In my case, it would be 6.2 volts. and you're going to screenshot this waveform. Yeah. So the next step it wants us to do is actually take a screenshot of that and include it in your report. And then make sure you're actually showing your cursors and markers when you do that. So show your peak-to-peak voltage. In this case, it's around 4.874 on the output. So at this point, we're getting diminished gain, right? Because we're putting in more voltage than we're getting out. So it wants us to look for, again, the place where the tops now start to saturate and the amplifier is totally in saturation mode. So let's go ahead and increase this to 5 volts, see what happens. Run it normal. Still haven't clipped on the top. So let's go ahead to 7 volts. And now we can see we've clipped on both the top and the bottom. So let's go ahead back down to 6 maybe. Yeah, we're already clipping on the top, so 5.5. Looks like about 5.5 is the place where it starts to clip on the top as well. So if we go ahead and run a single sweep, just so we can get a stable waveform, we can note the peak-to-peak voltage here. We can see that we're clipping so much that we're getting diminished return, right? Our swing is only around 7.261 volts, and we're putting in around 11 volts into the circuit here. So we're clipping off around 4 volts on the output. So make sure you have screenshots of both those output waveforms when the bottom or the top first starts to saturate and when the amplifier is totally in saturation. And you want to show your peak-to-peak voltages and your DC levels at the same time. So go ahead and do that. And then you should be done with this particular lab. So good luck on lab 4, guys, and we will see you again in lab 5. Bye-bye.